All right, we are back again. So as you can see on the slides, we actually have a pretty packed agenda. So we're going to continue with Arun's talk on benchmarking in the cloud. 50K transactions per second. That sounds pretty good. So why don't we just go ahead and start learning more about how to benchmark at this scale. Arun?
Hello, everyone. Good morning. Thanks so much for this opportunity to speak to you all. Hope you find it interesting. Let's start off with a quick introduction. I'm a performance architect. I've previously worked at Temenos and Cognizant, mostly in product performance and performance consulting roles. So recently, when I was working at Temenos, I was lucky to be a part of the team that delivered one of the largest benchmarks for a banking product, targeting 50,000 transactions per second. I don't know if you're all familiar with the banking space, so let me share some context. Temenos is the world's leading banking software company, and for this space, 50K transactions per second is massive. Even large banks do not do volumes in this range. Over the next 15-20 minutes, we'll be talking about this benchmark, some interesting learnings and insights. Indeed, there are a few insights that, looking back, I wish I knew earlier. Okay, so what was this benchmark all about? At a high level, it is simply about taking the latest Temenos software, the cloud-native, cloud-agnostic software, and deploying it on AWS Cloud, and seeing how far you can push the system, of course, with the defined hardware capacity. So we took Temenos Transact, the core banking product, and we took Infinity Microservices, the digital front office product, and deployed both in AWS Cloud, along with services like ECS, Lambda, DynamoDB, and NuoDB, the distributed SQL database. I'm really pleased to say we managed to get beyond the initial 50K target. We achieved 51,200 TPS. Let's take a look at the high-level architecture. First, the Transact components. With around 25% of the traffic flowing down this route, so the requests come into MQ, the Temenos software sitting in Docker containers in ECS, Amazon the Elastic Container Service, they read the request messages from MQ, process them using NuoDB backend, and reply back to MQ. NuoDB here is deployed as a multi-T, multi-SM layout. Then you have Infinity Microservices handling the remaining 75% load. These requests come into API gateway, Lambda spin up and service the request, and use DynamoDB as backend. Finally, you have the event streaming solution, which keeps Transact and Infinity in sync. It uses Kinesis data streams and Lambda. One key element of this benchmark was the requirement to do auto-scaling. So we wanted to prove that the software can support auto-scaling literally out of the box. So scale up and down with the load and keep the cost to a minimum. Moving on to the test infrastructure. We used a standard JMeter setup in a distributed mode with two load generator pools. So one for Transact and one for Infinity. One pushes requests to MQ for Transact, and the other pool pushes requests to the API gateway for Infinity. One quick point to add here, we generally tend to focus our attention on the system under test or the solution, and particularly when there's a scalability issue. Let me share an example from the benchmark. So we're hitting very high loads, and JMeter started reporting a lot of Amazon MQ errors. From the JMeter side, it seemed like Amazon MQ was not scaling up. And on the Amazon MQ logs, it was saying that the client, as in JMeter, was closing connections. After quite a bit of investigation, and initially we thought MQ might be the problem. We clarified that the problem was with JMeter. It is not able to handle more connections or requests per instance. Let's take a quick look at the monitoring setup. This is the same diagram that we just discussed through. So we have CloudWatch covering all the AWS services. As you probably know, CloudWatch is a good monitoring solution. Gives you a good view of the key metrics. In addition, we wrote some shell scripts to push JMeter stats into CloudWatch. We had a nice dashboard which gives a view of the transaction rate going up, the ECS and Lambda auto-scaling in action. It's too bad I don't have a screenshot to show. For NuoDB, we had Grafana dashboards. It exposes useful stats like the top events, commit rate, etc., which will really help you understand what's happening under the hood. And during the benchmark, we also had some excellent folks from NuoDB supporting us, helping us make sense of these metrics. And finally, for Lambda, there's X-ray distributed tracing. We'll talk about that in just a minute. Before we talk about specific layers or services, I wanted to talk about some general benchmarking considerations, mostly standard but important ones. So we'll quickly rush through them, but if you have any questions, please share. Firstly, benchmarks, of course, they need a lot of hardware. So you need to plan what instance types are optimal, how many you need, etc. You may need some quota or limit changes, account level limit changes as well. Also, scripts and automation to do test runs more easily, scaling down hardware when not required, etc. Data volumes. So of course, you need a lot of data. And for this benchmark, we had around 100 million accounts, 1 billion transaction records, etc. And this also means more time for database restores. For DynamoDB particularly, it was very slow. But with NuoDB, thanks to our NuoDB partners, we had some good quick options. Okay, so let's start with the individual components, ECS and MQ. As I mentioned, auto-scaling was really key to this benchmark. We don't want banks to pay for hardware that they aren't using, and we want our software to enable that. This chart is a representative chart. It's very close to benchmark actuals, but don't hold me to those exact numbers. Looking at the chart, we can see transact and infinity load. It slowly increases, it stays flat, and then it ramps down. For transact, this is possible because of ECS auto-scaling. Based on the current load, the CPU thresholds, ECS adds more containers and underlying EC2 instances. It's not all straightforward though. You need to work out the optimal thresholds, the time window to respond to changes, etc. For infinity, it's much more straightforward. Lambda is by design auto-scaling. You essentially just deploy your code and AWS does everything else, provisioning, scalability, high availability, etc. With Amazon MQ, there are a couple of parameters to consider: flow control, connections per protocol, etc. If you're unable to push high throughput and concurrency, you need to disable flow control and set a higher connections limit. Also, cost. MQ instances are quite expensive compared to EC2, almost 3x factor compared to EC2 Linux instances. So you can't be running them non-stop, particularly if you're not using them for your tests. But there's no shutdown option. So what do? You can create the required MQ configuration and save it. And when you require an MQ broker, spin up a new MQ broker based on this configuration. When you're done, you just delete the broker. Kinesis. In Kinesis world, shard is like CPU. More shards, more processing power, more events per second, and more cost as well. Each stream can have one or more shards, but each shard is limited to a certain read and write capacity. Again, CloudWatch helps out in terms of the key metrics and dashboards. You can, for example, look at iterator age to understand how long events are sitting in this stream waiting to be picked up, or latency, or you can understand if you're exceeding the capacity limits. There's also one interesting recent feature to call out. When you use Lambda as a consumer for Kinesis streams, normally you can only have one concurrent Lambda or batch per shard. So you can have a lot of events sitting in your stream, a lot of Lambda capacity, but still be blocked on the throughput. Of course, one workaround is to add more shards, but that's a costly workaround. Thankfully, this has recently changed. You can now specify multiple concurrent executions per shard if you want. I think up to 10 you can. Continuing on with Lambda, here you pay for the compute power that you use, but you cannot directly specify how much CPUs you want or the compute power you want per Lambda. Instead, you specify the memory capacity per Lambda and you get a corresponding CPU capacity. Around 1 vCPU for 1.8 GB of memory. This brings up a delicate balance. More memory gives more CPU and potentially better response time. More memory inherently costs more. Better response time also reduces the cost because you charge for the compute time. For troubleshooting, you can use CloudWatch and X-ray tracing. You can, for example, see if your requests are throttled due to hitting concurrent executions limit, or if your DynamoDB calls are impacting response time. You can see all those in X-ray tracing. With API Gateway, there's one key configuration to keep in mind, the endpoint type. You can configure an endpoint as either edge optimized or regional or private. If your clients are all distributed across geographies, edge optimized makes sense because the requests get routed to the closest point of presence. But if your clients are all in one region, example all JMeter EC2 instances in one region, the regional option gives the best latencies because all calls are intra-region. And finally, we are at the last component, DynamoDB. If you're getting bored wondering where is the thank you slide, don't worry, we're nearly there. To quickly introduce DynamoDB, it's a NoSQL DB from AWS, very fast, virtually infinitely scalable. The key measure of capacity for a DynamoDB table is RCU, read capacity unit, and WCU, write capacity unit. So supposedly, you can buy more RCUs and WCUs and scale infinitely, but not always. If you look at these charts, as the test progresses, and by the way, the load is increasing with time, read events are getting throttled. After the initial bit, more and more read events are getting throttled. Okay, so you look at the RCU chart. You can see consumed RCUs, it's going up steadily as we would expect with increasing load till around 3K, but no further. Provisioned RCUs is at 10K. So there's lots of capacity to spare and it's not being used. So what's happening? The problem is there is a limit per partition. 10 GB of space, 3K read capacity units, and 1K write capacity units. In this particular case, all the requests were just hitting the same partition, a hot partition. And with DynamoDB, AWS automatically decides the number of partitions per table based on a few criteria. So it's really important to ensure that a realistic mix of requests are used to avoid such hot partitions. There are other aspects like choosing a partition key, etc. But the general principle is that we need to ensure the requests are as spread out across the partitions as possible. Let's wrap this up with a quick look at some of the process aspects. They're all very self-explanatory and apparent, but looking back, you always wish you did better on these. First, have a clear, detailed view of what your benchmark goal is. The more detail, the better. Plan in detail how you'll get there. Start with optimized, scalable code and config settings. It's never a good idea to find and fix bugs during a benchmark. Plan for iterations, so the first time it's unlikely to all work. Make sure you have the automation, the scripts, and the monitoring to support you. And finally, keep an eye on those clouds. They aren't free. Thank you all for patiently listening. It's been an absolute pleasure talking to all of you. Thank you.
Awesome. Thank you, Arun. It's actually really cool demonstration of the power of using the cloud as well as the technologies that we have for benchmarking. Just recently been exploring some interesting modeling techniques used for universal scalability law and queuing theory, and it would be great if both of these things will be integrated at some point, such that the capacity planning and all these things just become a thing of the past. But for now, using functions and things like that definitely helps. Okay, let's transition to questions. So it looks like we have a question from Giovanni. So what were the main problems you addressed in scaling up JMeter to such a high load? Did you see problems related to JMeter load injectors reporting to the controller synchronously or with blocking batches? In my experience, this was something that hindered horizontal scalability in favor of more powerful instances.
Hi, Terence. Hello. Yeah, I was just replying to the question as well. There are two aspects. One from the load injectors to controller. There's an option to reduce the overhead. I think you can batch some of the traffic so that it's not too chatty. And in addition, per instance, I think we hit that quite a lot. I mean, not just for a benchmark. We cannot create more connections, or we can't do more traffic of a certain type per instance. So in this case, MQ, it couldn't create more connections from a particular JMeter instance to Amazon MQ. And I mean, that's in spite of any resource bottleneck. So CPU, memory, they were all fine. But I think there are some scalability limitations per listener, JMeter listener or JMeter instance, which you needed to look at.
Cool. That's great. Let's see if there are any more questions. Looks like we actually don't have any more questions. Come on, attendees, don't be shy. Please go ahead and ask your questions. Let's wait just for one more sec to see if anyone has any more questions. I guess I actually have a question. I wonder if you were aware of services like this that just do everything automatically. Like, for example, on Amazon, there is a marketplace where you can buy a lot of already built solutions. So is there a solution that someone can just go ahead and use for benchmarking that's gonna, create a good distributed benchmarking setup for you?
Not that I'm aware of, but I think it varies by solution. But once you have your layout clear, I mean, you can have, for example, CloudFormation or Terraform scripts to set up a whole benchmark environment and just change your configuration, for example, and run a whole benchmark.
Mm-hmm.
But that's repeating a benchmark. As in when you're doing it for the first time, there's definitely lots of variables and things to figure out, of course.
Yeah, I guess the biggest challenge is probably not even so much in terms of technology, but more in terms of understanding the domain to make sure that the benchmark is actually representative and produces the results that are useful instead of just bombarding service, because obviously you can just send broken data at the service and then you're going to get very, very fast responses with errors, which are probably not necessarily extremely useful for you. So I guess understanding domain and creating useful workloads for the benchmarks is probably the biggest challenge, and also something that requires domain expertise and not something that you can share as a generic solution.
That's true, isn't it? I think compared to benchmarking on-premise, the core part is not a lot different. You need to benchmark for the particular solution, the workloads, and so on. It's the cloud services, the things that work in cloud, do not work in cloud, those sort of considerations which we need to merge with the typical benchmarking aspects.
Yep, that makes sense. Okay, thank you so much, Arun. We are actually finally trying to catch up with time, so we're gonna have a quick break. So please come back at 10:35 to not miss the talk by Dmitry Pisklov. He's going to talk about microservices and single-digit microsecond latency. So that sounds super exciting. So don't miss it, and I'll see you in 2 minutes.